All right, well, good evening, and welcome to Kopernik Observatory. My name is Drew Desker. I'm the director here. It's great to see a crowd that would prefer to see a nice presentation than balloons going up here at Speedy Fest. No shade on Speedy Fest. It's a great time. I'll be there on Sunday, but they didn't launch today? All right, well, all right. Anyway, it's great to see you here all today. I always do this. I do a very quick survey. Who's here for the first time or not since your fourth grade field trip? All right, good portion of you. Excellent, excellent. All right, now, who here are members? All right, basically the other half. All right, that's great. What I like to do is I like to point out how the people who raise their hands second have actually a valuable piece of information is what a Kopernik membership can do for you. Kopernik, we're a nonprofit. And we do have memberships that allow you to come into Kopernik on a Friday night or any special occasions. And but also we belong to what's called the ASTC, Association of Science and Technology Centers. It's a consortium of more than 380 other science centers that share each other's memberships. So with your Kopernik membership card, you could go to Roberson. You could go to the Ithaca Science Center, the Museum of Science and Technology up in Syracuse, the Franklin Institute down in Philly, or the Intrepid down in New York City. Actually, another cool place is called the Museum of Mathematics down in New York City. Actually, I took my family there, and they actually have a little course with bicycles that have square wheels on it. That works. Because what you're doing is you're actually traveling on a track that is sort of got these little humps that just perfectly match. You wouldn't think it to look at it, but my daughters were just moving around just like nothing. So so if you like this kind of place, getting a Kopernik membership is actually quite a valuable thing. So Kopernik has actually been around for over 50 years. It started out as a celebration of the Polish astronomer Mikołaj Kopernik, who developed the heliocentric model of our solar system. And it opened, in 1973, Kopernik would have been 500 years old. And as I like to say, rather than buy a statue and plunk it in the park, they said, let's do something. So they built the original observatory, which was 2 of the domes. And actually, this brick building, this brick wall over here was actually part of the original building. It was donated to Roberson in the 90s. They expanded it to where we are today. But in 2006, Roberson decided running an observatory wasn't really part of their main business, so they were going to originally they were going to close it. But the Kopernik Society, that group of Polish immigrants who built the original observatory, said, "Look, if you don't want it anymore, we'll take it back." And so that's who runs the observatory. So we're a public observatory. We're actually, as a public observatory goes, we're actually probably one of the best suited and best sited public observatories in the Northeast. So we do, during the school year, we do a lot of school outreach, both schools coming to us as well as our educators going out to the schools themselves. We also do other public programs, like tomorrow down at the Vestal Library, we will be doing a planetarium show. We'll bring our portable planetarium down there and doing some presentations there. But this, during the summer now, we're doing a very extensive summer camp season. This year we've got over 200 students over about an 8 or 9 week period of time. We actually just a couple hours ago just finished a couple of camps. One on solar system exploration, another one on computer-aided design and 3D printing. Later this month we'll do another camp called Return to the Edge of Space, where our students will build a payload for a weather balloon that we will launch from here. It'll go up to over 100,000 feet when it finally bursts, and then the payload on a parachute returns to Earth, and we send a tracking team to go out and recover it. So we do a lot of fun stuff you wouldn't otherwise think school-age kids could accomplish. But then also on Friday nights, this is actually one of my favorite things is these Friday night programs. It's an opportunity to learn a little bit more about what the world is like. It's not everything we talk about up here is about astronomy. Tonight's program in particular is evidence of that. Actually, let me go and change here to get out of this. I was going to go back here and sort of point out our website. We always keep this up to date with what's going on. We actually have a 5K race for you runners or walkers. And even if you walk, you can do this, the Kopernik Race to the Stars. It'll be in September. Again, I talked about the summer camps. But our Friday night programs are an opportunity for us to learn something new. We've had people talk about the physics of music. Why does a violin, an oboe, and a trumpet all sound different playing the same note? We've had people from the National Weather Service earlier this year talking about the 32 tornadoes that happened in 2024. Tonight's program is going to be about ultra-flat materials, and we're very fortunate to have Binghamton University, and many of those researchers have actually come up here and done talks here. We've actually had a Nobel Prize winning chemist, Dr. Stanley Whittingham, actually do a presentation up here on the lithium-ion battery that he developed and ultimately became a Nobel laureate for. Later this fall, we'll have Carl Lippo talking about Easter Island and the moas, those big stone moas that, and they weren't carved out of where they were located. So they were carved and then moved literally hundreds of years ago. And how did they do that? So what's also nice about what we do here is we live stream all of these programs. It's an opportunity for us to continue our outreach. We now have almost 14,000 subscribers. Did this time lapse. Did this time lapse. And this was done with a telescope system called the C-Star, which is it's called electronically aided astronomy. You don't actually look through it. It's a telescope that just delivers the content directly to your phone or tablet or computer. Now here we are in full eclipse. We had to change the exposure so that we could see the full blood moon, which is really what you're seeing is the red light refracting through our atmosphere. It's not the end of the Earth. It's just a blood moon. It's just the red light refracting through our atmosphere. And then we're back to sort of standard exposure. Back in 2022, we had another lunar eclipse that we at one point had over 25,000 people watching our YouTube channel. And in the chat, people were saying, we left NASA's chat because we liked yours better. So Jenny Carty's been a great resource for us on that. So anyway, back to Friday nights. It really is an opportunity for us to learn more about what the world's about. Again, the world's a pretty big place, but I think tonight we're gonna get small.
Yeah, we're very small.
Get very small tonight. So Professor Zhong Lin, I met a couple of months ago, is here to talk about his work at Binghamton University. So let me get the display moved over to your computer, and off we go.
Okay. Yeah. Thank you everyone for coming to my talk, and thank you Andrew for giving me this opportunity to speak here. It's really a great pleasure to see so many families and coming to learn a little bit about physics. Today I will tell you something very superficial, very thin. This cartoon shows you more or less the topic we're going to be touching on today. You see those two kids are playing something just like a piece of paper. A piece of paper is apparently very thin, but there are other types of materials that can be much thinner than a piece of paper. And they are making a huge impact in the scientific community. I will show you a few examples why those very thin materials are interesting, both for science and for general people, and which kind of potential applications we can possibly have from those materials. Okay, you can interrupt me at any point. I try to keep the talk not so technical, but I welcome all kinds of questions from kids and from experts, okay? So I would like to begin my talk by showing you this very familiar tool that we use to write and we use to draw, right? This is a piece of a pencil. If you think about the core component of a pencil, which is the pencil lead, what makes up the pencil lead is a form of carbon called graphite, right? So if you look at the photo on the top right, you see the surface fairly reflective, and you see a lot of steps on the surface. That actually implies, okay, this graphite has a particular crystal structure. The carbons are arranged in a particular form. Scientists have actually looked into how those carbons arrange in graphite. They found, okay, those carbons form a layer structure. Within each layer, those carbon atoms shake hands, they form these hexagonal rings. You see there are a lot of hexagons, right, within one atomic layer. Those are very, very firm chemical bonds. The carbons really connect to each other very well. But between those layers, there are gaps. There are some empty space, right? So those layers are vertically stacked together. But the bonding between layers are fairly weak. The force is just barely enough to hold those layers together. But if you try to do something to it, you can easily separate those layers. That are actually possible. Okay, so here I'm showing you a different perspective of the same material, graphite again. This is image is taken by a high-resolution microscope called electron microscope. In part of the image, you see a very flat region in the middle. That is just one layer, but you also see many steps, just like stairs, right? Those features are telling you, okay, along the vertical direction, different layers are stuck together, just like how you can have a book that has many pages. Those are the edge of the book, right? One way to think about those kind of layer structure is they're just like a deck of cards, right? Collectively, they have a thickness that is quite considerably thick, but individually, there are so many pieces. Individually, they are really thin, and the forces that are holding those layers together are relatively weak. If you do something, you can easily slide layers against each other. Ultimately, it is possible to separate those layers. Have we managed to do so in our daily life? Yes. If you think about the very process of using a pencil to write something on a piece of paper, right? What are we actually trying to do, right? When we glide this pencil lead against a rough surface, right? We leave traces of this pencil lead on that paper. Essentially, we are leaving some carbon pieces, some layers of carbon, might not be very thin, but some layers of carbon on that piece of paper. We're essentially sliding layers and separating layers. Well, we have actually been doing some physical experiment since elementary school, right? So maybe we didn't think that way, but essentially that's what we have been doing all the time. Okay, so scientists also think about that process, and they ask a very simple, maybe a little bit silly question. If we work really hard, can we possibly just get one layer out, isolate just one layer, not 2 layers, not 5 layers, not 20 layers, right? So we want to push things to the limit, understand the very fundamental ones. Okay, 2 Russian scientists have actually figured out a recipe, figured out a trick to isolate just one monolayer of carbon atoms. And because of that contribution, they actually got a Nobel Prize in physics around 15 years ago. Whoa, the question sounds very simple, right? Maybe we could also do that. If you ask the right question, you have the right trick, and maybe you get a Nobel Prize, right? So, of course, they did something a little bit more sophisticated than how I describe it. They actually found when you manage to isolate just one layer of carbon atoms, those monolayers show some fascinating properties that people haven't thought about in the past. Today, I'm going to show you some of those interesting properties. So here I'm showing you the structure of a very thin carbon layer. On this particular image, I showed actually 2 layers. One layer is represented by the light blue balls. Another layer is in the dark blue balls. One is on top of another. Okay, so you see the orange sticks represent the atomic bonding, in-plane atomic bonding between carbon atoms. Those are really strong bonding. So those are 2-layer structure. If we separate them again, we eventually get just 1 atomic layer. Those are really, really, really thin. So nanometer is a unit that describes length. We don't typically use that in our daily life because it's so irrelevant to our daily life. We use meters and centimeters most of the time, right? But this material is so thin such that it is even less than 1 nanometer. It is 1/3 of a nanometer. Just to give you a perspective how thin this material is, I will start with something we can still imagine, then gradually get thinner and thinner. So apparently a human hair is very, very thin. Probably that is the thinnest object we can possibly grab by hand, right? Something smaller than that, we need at least tweezers to pick up, right? So the diameter of a human hair is on the order of 100,000 nanometer. The number is pretty large still. Now let's find something smaller. A biological cell has a diameter on the order of 10,000 nanometers. Still, many, many zeros after 1, right? Okay, let's get smaller. Next on the list is a bacteria. Bacteria is something we already cannot see with our naked eyes, right? We definitely need an optical microscope, at least, to see a bacteria. But if we use a nanometer ruler to measure the diameter of bacteria, it is a big object. It is 1,000 nanometer object, very big. Okay, let's get smaller and smaller. Next on the list is going to be virus, which is 100 nanometer. Then let's keep going down. Now we're reaching a regime around 10 nanometer and then eventually 1 nanometer. This ruler ends as 1 nanometer. Then you can think about, okay, this must be very, very thin, right? It's quite remarkable that scientists can precisely produce a subject that is so thin, and we are able to study that. We are able to detect some property out of that. Isn't that remarkable? Okay, so let me show you a few of the fascinating properties of such thin samples. From our daily experience, the thinner an object, when an object gets thinner, it gets more fragile, right? If you have a very thin piece of paper, okay, of course, you can easily break it if you are not careful, right? Initially, people think the same way. Okay, maybe it is impossible to get a monolayer carbon because it's going to break on its own. You cannot possibly stabilize that. Mechanically, it's so fragile. But actually, that's wrong. Experimentally, we found, okay, this monolayer graphene, its monolayer carbon is actually okay. It can be quite stable in laboratories. Some theories have even performed some calculation. They assume, okay, this monolayer carbon has no defect. They're trying to idealize the crystal structure, then found, in principle, you can put a big elephant standing on that just 1 atomic layer of material. It does not break. In reality, no one has done that experiment, so we don't know. We have not been able to make the monolayer carbon as large as the leg of an elephant, so we haven't done that experiment. But in principle, that's the strength you can possibly have. So it's something very remarkable, just like if you think about the spider web, right? It is so thin, but it's incredibly strong. That is one of the properties. Yeah. Another very interesting property is this is a monolayer carbon we call graphene, has remarkably high conductivity. So it conducts heat and electricity incredibly well. So let's first think about electrical conductivity. When we talk about conductivity, we naturally come to think about, okay, maybe metal wires are something we are familiar with, right? When we want to build a little circuit, we need a copper wire. We connect a battery, and electrons can flow. And then you get electricity. Okay. This monolayer actually can conduct electricity much, much more efficiently than most metals. Better than copper, better than gold, better than other metals that you can think of. Basically, when electrons move along this material, it basically does not feel too much resistance. It causes very little heat generation. Electrons can move almost freely over a long distance. So it's a very good conductor. At the same time, it is also a very, very good thermal conductor. Suppose I shine my laser pointer to a corner of this material. That little corner gets heated up. And then, within a very, very short period, that heat can propagate toward the other end of the material. Heat can travel really, really fast. This is a very good thermal conductor as well. That has been done, confirmed experimentally in the lab. Okay. So monolayer carbon is just one example of atomically thin, two-dimensional monolayer material. Over the past 20 years, scientists have discovered many, more than 100 materials that you can make it just one atomic layer thin. Here I'm showing you a different example. This is something studied by my PhD advisor. This particular sample is called tungsten disulfide. Each triangle here shows you a monocrystal. You can think of each one as just one piece of monolayer. We are looking at that vertically. And you see the edge looks red. That's right. They are optically very interesting. What we are trying to see here is we actually shine green light to those monolayers. And then, in return, those monolayers emit red light. This is a process called fluorescence response or photoluminescence response. Basically, those samples are optically active. They're quite funny. Only the edge emits stronger light, but the interior region does not emit that much light. So I'm not showing you a hollow triangle. Those triangles are solid, but the edge are optically very responsive. The interior region are not so responsive. Funny, right?
So,
yeah.
So what sort of applications in optical technology might you have with this?
Yeah, I will show you one.
Excellent.
Yeah, from this example, you can see it actually changes the color of what light you give it and turn that into a different color, right? That's something we call the photoluminescence. If I add a little bit of jargon, it's a direct band gap semiconductor. It has lots of uses for light emitting diode, for example. You could add a little bit of voltage to this monolayer. Boom, they will give you light. You will turn it on. That is possible. Yeah. Okay. Yeah. Feel free to ask questions. Okay. So I show you two examples, but actually there are a lot of examples. I think at some point you may ask me, okay, how can we possibly make those samples, right? Does that require a very complicated method to synthesize? Maybe you need some chemistry knowledge. Maybe you need some material science knowledge. Here I'm showing you how we grow that in our lab here at Binghamton. This is a glassware. And within this glassware, you can see some very shining reflective pieces with black color. Those are crystals with layer structures. What we do here is we mix some chemicals and seal them in this little glass container called a quartz ampule. And we put that in a furnace, heat it up, give it a little bit of thermal energy. This thermal energy will trigger chemical reaction. And after a few days, the crystals form within this little reactor. The length of this ampule is about 10 centimeters, just like the length of my finger. The diameter is about 1 centimeter. You can actually grab them. Those layer crystals are not so small. You can hold them with tweezers, right? But those are not two-dimensional. Those are still three-dimensional. There are many layers stacked together, okay? So this is the step one to produce a thin material. We start with something thick. Then we try to reduce the number of layers. That's what we do, okay? If you take it out, and look at that from the side, you can clearly see, okay, there are a lot of edges, lot of stairs, right? Those are indicative of the layer structure. Here again, I'm showing you an electron microscopy image, and again, even under a high resolution image, you see a lot of step edges, right? Now the question is, okay, now we have a very, very thick crystal to begin with. How do we make them thin? Well, just drag a pencil against the paper, right? Somehow find some trick to separate layers. Then maybe you are lucky, you find a monolayer. That's exactly how those two laureates tried at the beginning. Then they realized, okay, this method in principle works, but the efficiency is very low. Later on, they came up with an even smarter idea, which is to use a very cheap tool, the scope tape. I'm sure you all have that at home, but if you use that in the right way, you might get a Nobel Prize. Let me show you how how they use that. The black thing there, you can imagine that is a piece of graphite, right? Your pencil lead. Then you place this scope tape against the pencil lead. The function of the scope tape is it is very sticky, right? It's going to get some layers come again with it. When you peel the scope tape up, some layers will come together with the scope tape. Then, in this part, we have a flat surface. This is called a substrate. Actually, it's a silicon oxide substrate. What you don't have to know its function, but it's very, very flat. Right? Then you press this scope tape against this flat surface. Rub against it with your finger. Apply a little bit of force. Then peel off this scope tape again. By luck, some layers will come with the scope tape, but some layers like to stay with this flat surface. Okay. Then you can imagine, originally maybe you have 100 layers here, but when you split them, let's say 98 layers come up, 2 layers stay. Or maybe 99 layers come up, 1 layer stay. Well, then you have a monolayer. Right? That's how we do that experimentally. After that, we bring this flat substrate into an optical microscope. We look into this substrate carefully and check different corners. In some corners, we're not lucky. We get nothing left. In some corners, maybe we have 3 layers. In some corners, whoa, monolayer. Requires a little bit of luck and patience, but in principle, it does not take too much time. The whole process here takes about less than 1 hour. And if you sit next to a microscope for about 10 minutes, you might find a monolayer. And the monolayer is large enough to be viewed by a simple optical microscope. So this is how a monolayer looks like. This part, nearly transparent, is the monolayer. This part is something like a bilayer. This is slightly thicker. So the optical contrast, therefore the color, scales with the thickness of the sample. So monolayer is nearly transparent, but not exactly transparent. As you go thicker and thicker, they become darker and darker. So the color of the substrate is different from the color of the sample. Therefore, optically, you will be able to notice, oh, here I get something left over. That is the 2-dimensional sample there. Okay. So the scale of this flake is on the order of a few micrometers. It's not so small. The thickness is a few nanometers, but the lateral size is a micrometer. It's much, much greater. That's why we call it 2-dimensional. It's just like a piece of paper, right? If you have a piece of paper along this lateral size, it's probably tens of centimeters, but the thickness is much, much less, right? Okay. So here I have a little video showing you how to start with graphite and end up getting a monolayer carbon called graphene. Let me see if I can play. Okay.
Take a Scotch tape and gently lay it down on a flat surface. Next, take clean metal tweezers and pick a thin graphite flake, and then place this gently onto the Scotch tape. Next, fold the Scotch tape at the edge of the graphite flake. Peel it off gently and do this step several times until you obtain a nearly transparent region on the Scotch tape. After this, take a clean silicon wafer to transfer the Scotch tape graphene onto the wafer. Use plastic tweezers and gently rub the area of the Scotch tape where graphene may potentially be. Slowly peel off the Scotch tape so as not to break any potential graphene sheets. Use an optical microscope to view and find graphene. Graphene appears as a purple spot on the screen. At the center of the screen is multi-layer graphene, and at the right corner, lower right corner of the screen is single-layer graphene.
So doesn't seem so sophisticated, right? I wish I could have done that 20 years ago then, right? Okay. So now you're convinced it is possible to make a two-dimensional material, and if you use the right trick, it's not that difficult, right? So when graphene, the monolayer carbon, was discovered, people feel so excited. Okay, they immediately think about, there are many, many layer crystals, not just carbon, right? There are so many chemical compounds you can think of. Maybe we can play the same trick and generate a zoo of two-dimensional animals, right? Yes, indeed, that is true. Here I'm showing you some other animal. This is also a layered crystal. In this case, it's called tungsten diselenide. If you look at for example, this region, you see there's some seem like there's some steps, right? If you do the same trick again, you can turn that into a two-dimensional form. Extremely thin. It is possible. Okay. And all of those layer crystals share similar features. You see those step edges. Okay. So I received a question from the audience asking me, what can you do with those light-emitting, semiconducting monolayers, right? Now I'm going to show you one story from my own research. Okay, so here I'm showing you a cartoon. Does not seem relevant, but it's actually relevant. This worm is eating leaves, internalizing leaves. Okay, just keep that concept in mind, then I'll show you how that is relevant to my research here. So when I was a postdoc, we did a funny experiment. We chose some chicken liver cancer cells, and we placed that cancer cell on top of those light-emitting monolayers. And for some reason, those cancer cells like to eat those monolayers, and they internalize those monolayers as fragments, just like how you eat snacks. The funny thing is, because these monolayers can emit light, right? They are fluorescent. After this internalization, after this digestion, those cancer cells, like that, also become fluorescent. Initially, they are not fluorescent. After they eat snacks, they become fluorescent. Oh, that's very cool. So what that means is we introduced a method to optically label cancer cells, right? Imagine you have a population of cells, good cells, bad cells. We don't like cancer cells. We want to locate them, right? How do we do that? Hey, we let them eat some light-emitting monolayers. Then themselves become light-emitting. And they can actually pass these light-emitting properties to their next generation and next generations. So we can track them, track their grandson and grandson. So that's one of the funny applications. Then we thought about why those cancer cells can do that. It turns out the material being very thin is very critical. When the chicken liver cancer cell eats those monolayers, they are so thin, so the cancer cell don't even feel it, don't even get bothered. In some sense, those monolayers are not toxic to the cells. They just carry those monolayers everywhere without getting bothered by it. That's one of the interesting story I would like to share. Okay, there are other things we can do with these nice monolayers. Because we have a big library of monolayers, then you can treat them as building blocks, just like how you play Lego game, right? You have different colors, different choices. Naturally, you want to combine them and build something a little bit more complicated, right? You start with something simple, and you add complexity to it, right? Organize them, and the new functions will come up in the end. That's how scientists view those two-dimensional materials as well. Because we have a family of material. Each one has its own advantage, own function. We put them together and do something more complicated. A very active research area in the scientific community is called two-dimensional based electronics. What does that mean is, think about your cell phone. Your cell phone has a lot of components in it, right? Each one has a different function. You need some metals to conduct electricity. You need some semiconductors to do this logic operation. You also need some element to store information, like memory operation, right? And each two-dimensional material can serve as one particular function. And if you manage to put them together, combine them, you can actually build a circuit that can do some operation and do some memory functions. Each one cannot do, but if you combine them collectively, they can do it, okay? So how to do that? Well, that requires a lot of advanced instrumentation. Scientists typically work in an environment called clean room. They wear this very, very protective clothing. Therefore, there's no dust coming into contact with these sense samples. And the resulting device is super clean and is functioning. Okay, so one application that has been demonstrated is something called a light emitting diode. When we combine different two-dimensional materials, and some will emit this kind of color, some will give you a different color, and depending on how we apply voltage, how we combine them, we can make light, color-tunable light-emitting diode with a pretty good efficiency as well. And of course, they are very thin, so thin that you don't even think they are there. Okay, this is one of the application. Another very interesting aspect of two-dimensional materials is the very, very high aspect ratio. Along the lateral dimension, there are few micrometers across. Along the thickness dimension, they are less than 1 nanometer, right? This is extremely thin film. And the in-plane chemical bonding is so strong, it does not break easily, as I told you earlier. Therefore, you can imagine they must be very flexible. If you try to bend it, it doesn't break. If you try to roll it up, it does not break. So scientists are thinking, okay, what kind of application requires flexibility? Well, flexible display, flexible electronics, right? So two-dimensional materials are very, very promising in that regard. There are already some research activity going on trying to use them for flexible display, for touchscreen display. The hope is in the future, maybe your smartphone is going to get smarter. Your smartphone is already very smart, right? You can do a lot of things on it. But there's one thing you cannot do, which is to fold it, and put in your pocket. You don't have that capability yet, right? So sometimes we still complain, okay, the iPad or the tablet is a little bit too heavy. We hope it can get lighter, right? Maybe smaller, maybe easier to carry with, right? So in that regard, for the young audience here, maybe in the future, 20 years from now on, you have a smarter foldable electronics. When you need to use it, you unfold it. You have a big display. When you want to carry it, roll it up or fold it, put it in your pocket, right? It has not been realized. I'm just daydreaming here, but that is the active direction we have been researching on. Right? Okay. Yeah.
So you're saying folding it.
Mm-hmm.
That doesn't crease it. It doesn't break the connection when you actually fold it.
Yeah, it doesn't break the connection. Right.
Oh, okay. So later on,
Right. Right. So yeah, one way of thinking about it is to think about the curvature.
Right.
When we fold it, we thought we fold it 180 degree, right? But actually, when you look at the fold, that particular part still has a curvature.
Right.
And when the sample is so thin, it doesn't really feel the curvature. It's more or less folding like this, right?
So you want to be able to, I mean, there are certain things that if you folded enough back and forth, they would actually break.
Right.
But
Like something like a vertic, right?
Yeah.
Yeah.
But that's not going to be able to happen. With
Yeah, because it is so thin. When you fold it, it stays in the elastic regime. You can do many cycles, 10,000 cycles. It can still be, you can deform it and it will come back. Yeah. Okay. So another very interesting direction that layered crystals could potentially empower is energy storage. So I think Dr. Whittingham, the Nobel Prize laureate, will come at some point to give you a more correct talk on that topic, but I'm just showing you my personal understanding. If you think about lithium-ion battery, right? We store information, we store energy. We let energy flow into the battery, and when we need that energy out, the energy can actually flow out from the battery. What is the chemical process underlying energy storage and energy release? If you have a layered crystal like that, there are a lot of gaps in between layers. Therefore, you could allow some small ions to get in, to live within that gap. Through that process, energy is actually stored into that battery. You can do the reverse process. Let those ions flow out. Those ions can carry electricity, right? Therefore, energy can also flow out. So to have energy storage, we like to have a layer structure with some gap in between layers. Therefore, energy can go in or go out. So in that regard, layer crystals is going to be very important. There are a lot of active research going on trying to improve the energy efficiency. Okay, so why do we care about that? Because human drains a lot of energy, right? And probably you don't want to charge your cell phone once every few hours. Imagine if we need to charge our cell phone once per year. Wow, that's much better, right? If you have a hybrid car, you charge not every 300 miles, but 3,000 miles, right? That would make your life very, very convenient, right? So the way that we store energy in these layer materials is clean. We doesn't burn anything. We doesn't generate any smoke, right? It's a clean green energy. That is very important for the future generation. We don't pollute anything. Energy either goes in or goes out. No byproduct. Very clean. Okay, that's another interesting application. Another potential application of those monolayer layer structures is to filter polluted water. This has not been commercialized. It's a little bit of daydreaming, but there are active research on that topic as well. So polluted water consists of a big portion of the water we have on this planet, right? What is unique about layer materials? There are a lot of holes within the layer, right? Because it's not densely packed. You see there are spaces between those atoms, right? Those spaces are enough for waters to go through. But anything larger than that liquid droplet of water is going to be blocked. So it is a very nice filter in some sense, right? Yeah, probably you know in your house you have some carbon filter, right? This is the extreme version of that. Very, very thin, but still does the job, right? So this is another possible application. Biologists are also looking into two-dimensional materials with a different perspective. They have their own challenge in mind. They're trying to solve their own scientific question. So one of the application of two-dimensional material for biologists is to do DNA sequencing. This is an example of a graphene piece, monolayer carbon. It is possible to drill a tiny hole. This hole is also has a diameter of a few nanometers. This diameter matches the diameter of a DNA thread. Therefore, it is possible to let only one thread of DNA passing through at a given time. If you think about the structure of DNA, it has 4 kinds of bases, A, C, G, T, right? And what is funny is when this DNA is passing through, this monolayer carbon actually knows, okay, now A is passing, now G is passing, now C and T are passing. We are able to build a circuit around this monolayer carbon to monitor the electrical response. When different bases are passing, you receive different signal. It is quantized, digitized. Different base give you different trigger. It is possible to be read out. Okay, and since at any given time there's only one thread of DNA passing, we get a very clean response. Imagine you have 1,000 DNA passing together, right? It's going to be a mixture. It's very confusing. But here it's very simple. Only one at a given time. We can precisely determine the sequence of this long DNA thread. This is another funny application. So see, different scientists from different research fields are looking at two-dimensional materials with their own targeted application. Okay. So so another interesting application is to use two-dimensional materials to do logic applications. We have a large family of semiconducting two-dimensional materials. For example, in this case, is molybdenum sulfide. In research labs, you could connect that with some metal contacts. Therefore, we turn a material into a device. We are able to control the current flow within this device from a device, something like called a PN junction or field effect transistor. In simple language, we can dictate the direction for the current flow. If we want, we can say, okay, now we ask the current to go from left to right, not the opposite. Or we can do the opposite and say, okay, now the current can only go this direction, not the other way, right? From that, we're able to do a lot of and or logic operations. And all based on just a single layer of, single monolayer of molecules. You can do logic operations. You could also dream big and think about what has not been commercialized. So all of our devices, our computers we use nowadays are based on classic algorithm, classic operation. But there's a cutting edge direction in the scientific community called quantum computing, right? Quantum computing utilizes a whole different algorithm that is quantum mechanical based. The way to do operation, the way to do memory is completely different, right? In some sense, quantum device represent the future. A lot of the computation we need to do today requires too much computational resources. But if you have a quantum computer, that computation can be done, boom, within less than a second instead of 500 years, right? There are a lot of important scientific topics that we cannot do because we don't have that computational power. For example, we cannot predict earthquake or model the, for example, stock market or something complicated, more chaotic, right? Or we cannot design medicine very efficiently, right? Or we cannot predict new chemical reaction very efficient. But if we have a new computation architecture, maybe all those tasks become much easier to tackle. So in that regard, quantum chips represent a future direction. Two-dimensional materials also play a role in some of this effort. A lot of two-dimensional materials are magnetic, or they could be superconductor, or they could be even more exotic, something we call topological insulator. And in simple language, quantum mechanical properties are very, very enhanced in some of those 2D materials. Therefore, they could be highly relevant to this quantum business. Okay. Here I'm showing you, maybe this is my final slide. This gentleman here, maybe some of you recognize, this is Pichai, the CEO of Google. He's standing next to a big equipment called a dilution fridge. This is a cryogenic system that reaches a super cold temperature around millikelvin. What it does is trying to perform quantum computing. As we speak, quantum computing can only be carried out at a very, very low temperature, millikelvin, right? Almost close to 0 Kelvin. But we are hoping that quantum computer can be used just like your personal computer at room temperature, right? And not so big. So there's a long way. There's a long way we need to go. So providing new materials is a key component underlying this effort. Okay, and two-dimensional materials could potentially contribute to some of this future research effort. Okay, so with that, I hope I have shared some of my excitement about this topic with you and show some of the potential applications of two-dimensional materials. Okay, with that, thank you everyone for coming to the talk. And I'll be happy to take your questions.
Thank you very much, Dr. Zhong. This is why I love this thing. This Friday nights is like, you know, we're just getting started to understanding what the graphite can do, and I had no idea that there's medical, there's computational, there's
energy.
Yeah, unbelievable. Are there any questions here in the? We have one in the back. Give me a second. Wait a second. For the people on the live stream.
Maybe this is a little silly, but that single layer of the graphene that's in the cartoon there,
Yeah.
a single layer,
Yeah.
does it have strength in all
This one.
in all dimensions, like in all axes? Does it have strength this way, sideways? Does it, because you said it's very strong, the bonds are very strong.
Right.
But are they only strong in one direction?
They are strong. So let's call the thickness direction the z direction, and the 2D plane is the xy plane, right? They are strong along the xy plane primarily. So you can stretch it, but you can also fold it and try to bend it. So the in-plane bonding is very strong.
So you would be able to tear it?
You can still tear it. So in reality, I can tell you why you will be able to tear it. So no material is perfect. There are always some defects. Along the defects, it's very easy to break. Once you make a tiny crack along the defect, it's going to propagate and break the whole thing.
Oh, hold on, another question.
Not really a question, but I've heard that a sheet of graphene is harder to tear apart than solid steel.
Depends on how you compare them. So in some sense, when we compare monolayer graphene with other materials, we assume if the thickness is comparable, right, then we apply this much force, then that comparison is fair. But I assume the stainless steel is having a diameter about maybe a millimeter or centimeter, then it's not a side-by-side comparison. But if we scale them into the same scale, graphene is quite strong.
So here's a different question.
Oh, yeah.
Steel is very good in tension.
Right.
Concrete is very good in compression.
Mm-hmm.
So for these single layer things, does it matter whether you're doing?
We were not able to apply compression easily because we cannot, hold the edge and squeeze it. What we could do is to apply tension. For example, we can put them on the substrate. Therefore, we can grab the edge and stretch it. they can hold like a few percent of strain, tensile strain, no problem. They don't like to be compressed. If you compress them, they buckle up. They buckle up.
Any other questions? Oh, hold on. We got one over here.
When you had the microscope pictures up, the magnification said 11K.
Yeah.
What was the X after it?
Oh, this thing? You're talking about something like that, right? Yeah. So it's 7,000, around 7,000 along this dimension. So what you are looking at is something on the order of a few micrometers across along this X or Y direction. This is the electron microscopy. It's slightly conceptually different from the optical microscope where you have magnification printed on the objective lens. It's slightly different. It also matters about something like a working distance, but I don't want to get into detail. But there's a few micrometers across.
Another question over here.
Yeah, how close are you to being able to mass produce? I mean, how easy is it to mass produce the graphene?
Yeah.
How much Scotch tape do you have, I guess?
Yeah. So here I only have 1 hour talk. If you give me 3 more hours, I can show you a different way of making graphene. So the way I showed you is start from something thicker and you make it thinner and thinner. There's an opposite approach where you start with an empty substrate and you try to add some atoms into the substrate, hoping that they form a monolayer automatically. This is a process called bottom-up approach. That approach, which I didn't mention, is much more scalable. And that's something industry is trying to do.
So we're able to mass produce right
We are
now?
able to mass
So
produce.
we're really close to making those phones you were talking about.
So I can tell you, in laboratories, they can make monolayer graphene on copper foils. Copper is the substrate. So the limitation of the size of graphene is dictated by how big your copper foil is and how big your furnace is. If your furnace has a diameter, let's say, this big, and your copper foil is like a piece of real paper, then the entire surface can be covered by monolayer graphene, no problem. But there are some challenges, but it is possible.
Another question over here. This is great.
When it shows the picture up there with the layers, are those ones that are right next to each other able to see, or is this one that's like really close up that the human eye can't see by itself?
So I was a little bit, could you rephrase this?
Like, can you without a microscope or anything, would you be able to see those tiny ones?
You will get some indication. For example, if you look carefully here, right, there seems like there's some layered terraces, stairs, right? I can show you another example earlier, this guy. But each step is not going to be a monolayer. Each step, maybe here is 2,000 layers, here are 5,000 layers, 10,000 layers, big steps.
Yeah, but I'm wondering, like, on the flat parts of it, it's like some of them are flat. If they're like really tiny layers that are on top of them.
There could be.
Okay.
Yeah. So they are flat to our eyes, but they might not be so flat locally. Yeah. There could be still some thickness variations. Yes.
I'm not entirely sure if I'm remembering this right, but I do believe they found naturally occurring monolayer in a cave. Something about a bacteria that produced a monolayer of graphene.
Bacteria produce monolayer graphene.
Yeah, this was this took thousands of years to produce, and again, I'm not entirely sure. It wasn't very pure. It was like maybe 10% pure, but it was still a monolayer of graphite or graphene, whichever one it is.
Yeah, I don't know that study, but it might be possible. So I can share you a similar story, a famous one. So in the outer universe, the cosmic ray carries energy. They can naturally produce a form of carbon called brachyfluorines. the soccer ball form of carbon that is naturally produced in outer space. That was a Nobel Prize around 1985. So nature can do a lot of funny things, right? Biological system can create molecules or materials in their own way that sometimes we don't fully understand, but it's possible. But I don't know that particular study.
Right, another question back here.
Was Corning's discovery of the photogray process in any way related to cell technology like this?
You mean Corning's?
The Corning photogray glasses, how they change with the sun exposure, light exposure. Wonder if there's any connection.
When they're exposed to light, when the cells are exposed to light, they darken. So if you're in a room like this, you have clear lenses. If you go outside in the sunshine, they darken. And I wondered when you mentioned the red-green change, if it's any way related.
I don't have much knowledge on that, but I think that is more likely a reversed chemical reaction process. Light triggered like silver oxide and changing to something like that. It's more likely light catalyzed the reversible chemical reaction. Here, I think you were referring to something like this, right? Likely a different mechanism. Here's a process called photoluminescence. Essentially, the sample absorbs a photon and promotes electron to go to a higher energy. When that releases back, it releases another photon of different color. So essentially, this is something related to the band gap of material. And this color does not change. And it's not a reversible bistable state. So the process you described is more like a pneumatic reaction type of thing, where there are two possible states. You can either make it darker or make it more transparent, right? And it's reversible. There's a trigger to do that. Slightly different, I think.
Right, any other questions? Well, our friend Lindsay, for those that come here on an ongoing basis, there's a woman in Adelaide, Australia, who basically, she's one of our top fans and is watching today from Adelaide, Australia. So everyone say hi to Lindsay.
Hi.
All right. She's finishing up her breakfast right now. But anyway, thank you very much. This was an outstanding presentation, and I'm going to definitely have to start doing a little more Google searching on this. This is great.
Thank you for everyone.
So, yeah. And as always, great questions. Appreciate that. So we have a rule here at Kopernik that, especially if this is your first time, you can't leave until you look through a telescope. So we're going to ask you to put your keys up here, and then when you're done, you can. Now, but the moon is going to be out tonight. We're going to have a nice clear sky. So we invite you to head out to into the domes. We'll have some scopes out in the yard. I'm going to actually have try to get one of our scopes set up to look at the moon, but it'll have a cell phone adapter on it. So we'll work on trying to get your cell phone to actually take a nice picture of the moon through one of the telescopes that you get to take home. All right, so thanks again, and we'll look forward to seeing you up here again soon.
Thank you.